Hey guys, and welcome back to this class, Bayesian Machine Learning in Python, Part 1. In this section, we're going to start looking at Bayesian methods. This lecture will look at some motivation behind why Bayesian methods are beneficial, in particular the explore-exploit dilemma. We won't jump into Bayesian methods right away, but rather we'll discuss the disadvantages of using traditional A/B testing. You'll recall that in the last section, I showed you an extreme example with medical drug testing for why you would not want to do a traditional A/B test. If you are absolutely certain a drug is working well, and you know it could save or greatly improve the quality of life for all your participants, you would be very tempted to stop your A/B test and give everyone the drug. But frequentist A/B testing says to not do that. Recall why it's bad to stop early. It's because it's possible for an A/B test to show significance when there isn't any, which we call a false positive. It's also possible for the p-value to go below the significance threshold and then back up. To illustrate this point further, I'm going to use a more traditional example from Bayesian A/B testing literature. We call this the multi-armed bandit problem, and it goes like this. You are at a casino, and you are playing the slot machines, hence the term arm. And they are bandits because they are taking your money. Not all of the slot machines are equal, so one might give you a prize 30% of the time, one might give you a prize 20% of the time, and another might give you a prize 10% of the time. Well, this is the same problem as click-through rates or conversion rates. You'd set up an A/B test, run your experiment, and by the end of it, you would know if any one arm is significantly better than the others. But the question is, would you really do that in real life? Even after something as small as 3 plays each, if one arm gives you a prize 3 out of 3 times, and another arm gives you a prize 0 out of 3 times, you will probably just want to play the first arm more often. In other words, you want to adapt to the data you've collected so far. Keep in mind, 3 plays is probably not enough to attain statistical significance, and yet you still feel compelled to believe that the first arm is better. Now, just as an aside, this is the same problem we face in reinforcement learning. When you're trying to teach a machine to play a game, it's going to model the rewards it gets based on the actions it takes. The problem is, this process is possibly stochastic, and your model of the rewards is only an estimate. Furthermore, in certain games, it's not computationally feasible to try every possible action in every possible state, so your reward estimate is only approximate. Early on, when you haven't taken too many actions yet, you'll know almost nothing about the reward structure. So you can't really choose the action that has given you the best reward so far, because your knowledge about what actions lead to what rewards is minimal. Only after you collect a lot of data can you be more certain that your estimation of reward is accurate. So this problem has a name, and it's called the explore-exploit dilemma. The question is, if I've gotten 3 out of 3 prizes on one bandit, and 0 out of 3 prizes on the other bandit, should I exploit the first bandit more, or should I explore so that I can collect more data and be more sure about each bandit's win rate? The coming lectures will look at several solutions to this problem. While they are all adaptive, they are not all Bayesian. We'll look at the Bayesian method last, and it'll help you understand and appreciate the elegance of the solution. Hey guys, and welcome back to this class, Bayesian Machine Learning in Python, Part 1. In this lecture, we're going to do a demo to see how the click-through rate converges to the best bandit when we use the Bayesian bandit method. So let's start by importing matplotlib. Let's import numpy as np, and we're going to make use of the code we wrote earlier. So from Bayesian bandit, we're going to import the bandit class. Next, we'll have a function to run experiment. It takes in 3 probabilities, so there are going to be 3 bandits, and number of trials. So we are going to define each bandit. And we're going to keep track of all the data we get. So it's either going to contain 1 or 0, 1 for click, 0 for no click. We loop through n. We get the argmax of the bandit samples. Okay, and that's the arm we pull. So x is equal to bandits of j dot pull, and then we update bandits of j. We also want to keep track of x, so that becomes data at I. Next, we want the cumulative average. So NumPy gives us special functions to help us do this, so you don't have to do it manually. You do the cumulative sum of all the data, and you essentially divide by the n at that point. So that's just a range n plus 1. Okay, now we want to plot all this stuff. So we plot the cumulative average, and we want to plot each of the probabilities. So that's NP of 1s of size n times P1. And we do the same thing for P2 and P3. And now the probabilities are going to be pretty low, so we want to keep the range of y from 0 to 1. So we pass in 0, 1 like that. And also there are going to be a lot of samples, so if we do a log plot on the x-axis, it looks a little nicer, easier to see. Okay, and then we show the plot. Run experiment. Feel free to try different values if you want. We're going to run this for 100,000 samples. And let's do one quick fix. And now let's run this and see what we get. Okay, so you can see that in the long run, approximately after 10,000 samples, we have converged to a click-through rate of 0.3, which is our best bandit. Hey guys, and welcome back to this class, Bayesian Machine Learning in Python, Part 1. In this lecture, we are going to answer the question, just how accurate was the confidence interval we derived earlier? In particular, we are going to visualize the approximated Gaussian that results from the central limit theorem and compare that to the Bayesian beta posterior. This is all similar to code we've written before, so feel free to try this yourself first. If you don't want to code along, the relevant file is ci-comparison.py. So let's start by importing matplotlib. Let's import NumPy. And from scipy.stats, we need beta and norm. So the number of iterations we're going to do is 501. The true click-through rate will be 0.5. We're going to set our beta priors to be non-informative, so they're going to be 1 and 1, which is the uniform distribution. And plat indices. This is going to tell us when to plot. Okay, and then we're going to have an array to store our data. So for I in x range t, we draw a sample. So we're just using a click-through rate of 0.5. Actually, we can use true CTR for that. Okay, we'll store the sample we gathered, and we'll update the beta distribution. Okay, and then if I in plot indices, so then we have to do a plot. So our estimated click-through rate is data up to I, and then we calculate the mean of that. Number of samples is I plus 1. So the standard deviation of this is the square root of p times 1 minus p divided by n. Next step is to plot the Gaussian. So we create our x-axis. So I'm rewriting the old x, but it doesn't matter since I'm not going to use it again. So this will be the PDF of the Gaussian. The mean will be p, of course, and the scale will be STD, which we just calculated. We plot this and give it a label so we know what it is. This is the Gaussian approximation. Next, we do the same thing for the beta. So the posterior is beta PDF, x a equals a, b equals b. We plot this, and the label will be beta posterior. Call legend so the legend shows up, and we'll give it a title. We'll say what n is so we can keep track, so we know how many trials we've done. And we call plt.show. Okay, so that's all the code for this. So let's run this and see what we get. Okay, so at n equals 11, the Gaussian approximation and the beta posterior are pretty different. At n equals 21, they appear to be converging. N equals 31, we see the same behavior. N equals 51, even closer. N equals 101, now they look almost the same. N equals 201, even closer. And the last one is n equals 501, so they are pretty much equivalent at this point. This is also a demonstration that the central limit theorem is true, by the way. We can also zoom in, see how close they are. Let's make this window a little bigger. Okay, so you can see that we're very, very close. Hey everyone, and welcome back to this class, Bayesian Machine Learning in Python. In this lecture, we're going to practice the Bayesian bandit method on the same click-through rate data we used earlier. Now right away you should recognize that there's a problem with this exercise. It's mostly conceptual. Let's see if you can figure it out. I'll give you a second to think about it, or you can pause this video and come back later. Okay, so hopefully you thought about why this exercise might be a little strange. Recall that earlier we assumed that our data was stored in a file. That means all the data existed before we even ran our analysis. The Bayesian bandit method is different because it operates in real time. It is adaptive. Sometimes people call this online learning. It's going to show an advertisement based on the data it has collected so far. This is vastly different from what we were doing before. Luckily, I've already written a script to simulate this process so you don't have to. It's going to run as an HTTP web service, just like you would use on a real website. So this is a very practical exercise since it shows you exactly how you use this on a real website. So let's look at diagrammatically how this is going to work. On one end, the right side, you have the server side, you have the bandit algorithm. This decides which advertisement the client is going to see. So at first, with no data, it's of course going to be completely random. Then the user, which is on the client side, decides whether or not they're going to click on this ad. We can pretend that the client actually represents multiple users clicking on the same ad, and that whatever they do on the ad, whether that's click or no click, that they're representing what real users would do when they see this ad. Of course, really, it's just pulling from the dataset file that we already know exists. Once the server receives that action, the algorithm updates its beliefs about the click-through rate of that advertisement. And this just continues on forever as the server collects data about the advertisement it shows. But remember, it's adaptive, so the advertisement it chooses to show is based on its beliefs about the click-through rates of each advertisement. So the next time the server shows an ad, it's going to use what it has learned about each of the ads to show the one that is more likely to be clicked. So how do you complete this exercise? Well, first, you have to know how to run the client and server. Of course, the server must be running before the client tries to make a request, so you have to start the server first. That's python server starter.py. Then you can start the client. That's python client.py. So right now, the server is very dumb and is not running the Bayesian bandit algorithm. It's just returning the same advertisement every time. That's server starter.py. It's designed so that you don't have to write the server code, since this is a machine learning class and writing server code is just boilerplate stuff that's not relevant to machine learning. So all you need to do is write the relevant parts to serve the advertisements in an intelligent way. Basically, wherever you see a to-do, that's where you'll probably have to fill something in. So your job in this exercise is to modify the server code in such a way that it will run the Bayesian bandit algorithm you learned about in this course. The client is just client.py, which requests ads and clicks on ads using the data file we were using earlier. This requires no change because our data set is fixed. If you want to look at the solution, that's in the file serversolution.py. As an extension to this exercise, you can also try implementing other algorithms we talked about, such as epsilon greedy and UCB1. Remember that the server code will remain the same because all algorithm interfaces are the same. Only the algorithm itself will change. This is a key concept. Now remember that all data is the same too. So if you were wondering, well, how does this apply to my data? Then the answer is, of course, well, then you'd hook up your data into this same algorithm. Like I said earlier in the course, we're pretending that this data represents clicks on advertisements, but that need not be the case. They can represent article headlines, or they can represent logos, or whatever else it is you want to test. The possibilities are endless. So as an extension of this exercise, you could try this on your own data, for example, if you run a website. This is not a machine learning task, but rather just a regular programming task. In fact, this is one of the most easily applicable algorithms in the real world. It's very easy to start a website these days, and anyone with a website can use this method to try something like testing 2 different logos. Hey guys, and welcome back to this class, Bayesian Machine Learning in Python, Part 1. In this lecture, we are going to build on our mathematical tools in preparation for Bayesian A/B testing. Way back in an earlier section, I talked about the Bayesian paradigm. I said that the frequentist paradigm is that when we measure parameters like the mean or like the click-through rate, we are doing point estimates. We sum up all the results, divide by n, and that's the estimate. This was a problem because it didn't take into account how certain we were about those estimates. However, the solution was we could use the central limit theorem to show that the confidence interval is approximately Gaussian, and from there we can get an upper and lower bound on the 95% confidence interval. So the frequentist paradigm calculates the likelihood, maximizes the likelihood with respect to the parameter in question, and that's how we get the maximum likelihood estimate for that parameter. In Bayesian statistics, we treat the parameter as a random variable too, so it has its own distribution, and the shape of that distribution will tell us how confident we are of any value for that parameter. In particular, we apply Bayes' rule to help us with this. We say that the distribution of the parameter given the data is equal to the probability of the data given the parameter times the prior probability of the parameter divided by the probability of the data. Recall that we just think of the denominator as a normalizing constant, since it doesn't depend on the parameter theta. To remind you, the three key pieces of the Bayesian equation all have a name. The posterior, which tells us our new belief about the parameter after collecting data, the prior, which reflects our old beliefs about the parameter, and the likelihood, which tells us how likely it is we saw the data we collected, given our old belief about the parameter. So you might be thinking, well, that's pretty easy. It's just multiplication and division. But not so fast. We are not multiplying and dividing numbers here. These are all probability distributions. In particular, you'll recall that the thing on the bottom is the integral of the thing on the top over all settings of the parameter. Generally speaking, this integral is either hard or impossible to solve. One solution to that is to use sampling methods like MCMC, but we won't cover those in this course since we are going to arrive at a much more elegant solution. The answer to our problem is conjugate priors. What does this mean? Well, it turns out that for specific likelihood distributions and for specific prior distributions, when you solve Bayes' equation, the posterior distribution will be the same type of distribution as the prior. So let's do an example to illustrate this. We know that our likelihood for click-through rate is Bernoulli. We also know that theta must be a parameter between 0 and 1, because it's the probability of getting a click. Well, if you browse through a list of probability distributions that can range from 0 to 1, you might arrive at the beta distribution. In particular, the PDF of beta is theta to the power of a minus 1 times 1 minus theta to the power of b minus 1 divided by the beta function of ab. And the beta function can be defined in terms of the gamma function, and the gamma function is a generalized form of the factorial function, but it works for any real number. Now let's combine the likelihood and the prior using Bayes' rule, and see if we can solve for the posterior. So we use the proportionality symbol because we're not considering the normalization constant. We can combine like terms, so everything that has theta on the base goes together, and everything that has 1 minus theta on the base goes together. And then we realize this has the same shape as the beta distribution. Remember that the normalization constant doesn't matter because it does not depend on theta. In particular, we can see that p of theta given x is also a beta distribution, but the parameters are a prime and b prime, where a prime and b prime can be defined in terms of all the x's we've collected, or we can phrase it in terms of our click-through rate problem. One interesting fact about the beta distribution is that the mean is equal to a divided by a plus b, which is exactly what the maximum likelihood estimate of the click-through rate would have been. However, this solution is much more elegant because this distribution doesn't require an approximation. Another interesting fact arises when we analyze the variance of the beta. So what's interesting about this? Well, we know that the more data we collect, the bigger A and B will become. Therefore, as A and B get bigger, the variance gets smaller. So this automatically follows the same behavior we observe with the approximated confidence interval, which is that the variance shrinks as we gather more data. One question you might have is, well, how do we choose the original A and B? It turns out if you set A equals 1 and B equals 1, the beta distribution is equal to the uniform distribution. This makes a lot of sense because if you don't know anything about your click-through rate prior to your experiment, then all possible click-through rates are equally probable. We call this a non-informative prior. One important fact is that as we collect a large amount of data, the influence of the prior parameters becomes negligibly small. So let's summarize what we just did. We first recapped what it means to be frequentist and what it means to be Bayesian, where we treat the parameter we are measuring as a random variable and give it a probability distribution. We identified a set of probability distributions, the Bernoulli and the beta, such that when you combine them using Bayes' rule, the prior and the posterior are of the same type of probability distribution. We call these conjugate priors. If you're interested, Wikipedia has an article on conjugate priors that lists out all the likelihood prior pairs that go together. I found it to be a very useful reference when doing Bayesian statistics. Lastly, we showed that the beta distribution naturally has the same mean as the maximum likelihood click-through rate, and that the variance automatically shrinks as you collect more data, just like with the frequentist confidence interval. Hey guys, and welcome back to this class, Bayesian Machine Learning in Python, Part 1. In this lecture, we're going to finally take a look at the Bayesian A/B testing algorithm. In the last lecture, we looked at how we can get a probability distribution on our click-through rates given the data we've seen. Now the question is, how can we use these distributions to 1. Solve the explore-exploit dilemma, and 2. Do it better than epsilon greedy and UCB1? The answer to this is sampling. Whenever you generate random numbers, you have to ask, what distribution am I sampling from? Typically, most programming languages give you a rand function that provides you with a uniformly distributed number between 0 and 1. NumPy also gives you a rand_n function, which lets you sample from a Gaussian with mean 0 and variance 1. Unsurprisingly, SciPy allows you to sample from all of the distributions that it contains, the beta distribution being one of them. So the question now is, how does sampling from the beta distribution help us? Well, let's consider a few scenarios. The first scenario is when we have already spent a lot of time exploring, so we have pretty sharp, small variance estimates of our click-through rates. Well, if we sample a number from both of these beta distributions, we would expect with very high probability that the one with the higher click-through rate will give us a larger random number. So in terms of our Bayesian bandit problem, we should choose to play the bandit that gives us the largest random number. Note that it is still possible for the worst bandit to give us a larger random number, but as the variances get skinnier and skinnier, this will become more and more unlikely. Now let's consider another scenario. One bandit has been exploited a lot, so we are very sure of its click-through rate, but we haven't collected so much data for the other one. Sampling and choosing the maximum helps us here too. Because in this scenario, the bandit with the fatter variance has a much higher chance of giving us a random number that is larger. So you see that it's the distributions themselves that tell us how much to explore or exploit. More data gives us less variance, which gives us less exploration. Less data gives us more variance, which gives us more exploration. Let's look at this same scenario again. Notice that the sharp click-through rate is pretty high. If you split the fatter distribution along that higher click-through rate, you see that it's more probable to choose a lower number than it is to choose a higher number. What does that mean? It means that the sharp CTR bandit is already pretty good, so we will spend more time exploiting that and less time exploring. Compare that to if the sharp CTR was lower. In that case, the probability of exploring the other bandit would be higher because more probability weight is to the right of it. Note that this method is also referred to as Thompson sampling, and it can also be used in the context of reinforcement learning. So perhaps we will cross paths with this algorithm again. Now let's put that all together with some pseudocode. So in a loop, we draw a random sample from all the bandits. We choose the bandit that gives us the maximum sample. We then pull that bandit's arm, and then we update its A and B. Note that this is totally independent of how many bandits there are, which was one of the things we needed to correct for with the frequentist A/B test. Next, we'll look at how we can do this in code, and we'll observe how the beta distributions evolve over time. Hey guys, and welcome back to this class, Bayesian Machine Learning in Python, Part 1. In this lecture, we are going to code the Bayesian A/B testing algorithm. If you don't want to code along, check out bayesianbandit.py in the class repo, and you can just run this file. So let's start out by importing matplotlib. So we're going to make use of visualization in this example. Let's import NumPy. And let's import the beta distribution. So let's set the number of trials to 2000. I'd recommend playing around with that. And also abilities. Play around with this too. The true click-through rates. Okay, so I'm going to define a class called bandit. And it's going to basically act like a slot machine. So it has its probability of winning, self.p equals p, and then it has its beta parameters, so A and B. The priors will be 1, so that's a uniform distribution. Have the ability to pull the arm of the slot machine, and that returns a random number. Right, so if it's less than p, we get 1, otherwise we get 0. And we can also sample from its current beta distribution. And then lastly, we have a function to update its A and B. So this is the formula we derive when we were looking at conjugate priors. So x is either 0 or 1. Okay, next let's define a function to plot each bandit. Trial will be the trial number. Okay, and so this is just going to plot the PDF of each bandit so we can compare them on the same chart. So we know it's between 0 and 1. Let's give it 200 points so it looks reasonably smooth. For B in bandits, calculate the y values, b.a, b.b, and then we do a plot of the PDF. And its real p is of course b.p. Okay, let's give it a title. Bandit distributions after this many trials. Make sure it shows the legend and plt.show. Next, we'll write a function for actually running this experiment. So we're going to call it experiment. I'm going to initialize an array of bandits. So each has its own P for P in bandit probabilities. Sample points. So these are the points where we want to show a plot. So that's 5, 10, feel free to add more, 20, 50, 100, 200, 500, 1000, 1500, 1999. Okay, and then we're going to loop through each trial, set best B to none. So this is going to be the bandit whose arm we eventually pull. Max sample, so we keep track of the maximum sample we got. And then all samples, this is just for debugging purposes, so we can print out what we sampled from each bandit. So we loop through each bandit. You could use argmax for this, it would be much simpler, but we want to print some debugging information. So we sample from the bandit. We append the sample to all samples. And if this sample is greater than the current max sample, we set max sample to this sample. So we keep track of the maximum, and best B will equal B. Okay, if I in sample points, then we should plot. And also debug, so we print current samples. So we call plot, bandits, and then I is the trial number. Okay, once we've chosen the best bandit, we want to pull its arm. So X is equal to best B dot pull. And once we have a result, we want to update that bandit with new information. Okay, and let's write some code to run this. If name equals main, run the experiment. So let's run this and see what we get. Okay, so we see that after 5 trials, all of the variances are pretty large. This is after 10 trials. So red is still the highest. It's still not quite sure where the click-through rate is, but it's higher than everything else, which is what we want. This is after 20 trials. So we are now becoming more certain about the click-through rate of red. Okay, so we're not so accurate with green. We have some probability weight higher than red in green, even though the true click-through rate is 0.5. So that's just due to the randomness of the problem. So at 100 trials, green becomes lower, closer to its true value. Okay, 200 trials. 500 trials. So notice how red is getting really sharp. Green and blue are still pretty fat. 1,000 trials. Green and blue are still pretty fat. Red is getting still sharper. 1,500 trials, same pattern. And this is the last printout. So green and blue are still pretty fat, and they're on the left. So the interesting thing to observe here is that the lower performing bandit distributions never become sharp. They stay relatively fat compared to the best bandit, but even so, most of their probability weight is in a range less than the best bandit. In other words, we are almost certain that the true click-through rate was lower, and because of that, there's no need to explore further to improve those lower estimates. Hey guys, and welcome back to this class, Bayesian Machine Learning in Python, Part 1. Let's step back for a bit and consider how far we've come along. We started off with the traditional A/B test, where you have to do all sorts of approximations, awkwardly decide how many samples you need to collect with more approximations, and then run your experiment to full completion without adapting to the results you collected so far. If you want to stop early, you won't get a valid result, according to frequentist statistics. Now we have a way to create an adaptive system that actually, if you think about it, doesn't even require any kind of test. You just start your system and let it run, and eventually it converges so that you are doing the best possible thing given the data you've collected. There's no threshold at which the results become valid. You just naturally converge to equilibrium. One interesting aspect of the Bayesian sampling method is that your measurements become more accurate after every single sample you collect. How is that? Well, if you were paying close attention to the code, you would have recognized that we didn't just update A and B after collecting all the data, but instead we updated it every time we pulled an arm. In other words, the posterior we have now becomes the prior when we incorporate even more data. Compare that to a traditional machine learning model, where you fit all your training data at the same time. And then if you want to add new training data, you have to start training again from scratch. With Bayesian methods, all we had to do was add a number to A and add a number to B, and the beta distribution, since it depends on A and B, is automatically fine-tuned. This is an example of online learning. The model learns after every new sample. There won't be any RAM issues because A and B take up constant space. Because of that, there won't be any speed issues either. In a sense, this is more similar to how humans and animals learn too. We take our most recent experience and we try to form some opinion about it. Never do we think about every experience we've ever had and try to get to some global optimum. In fact, we can't do that because our memory systems are imperfect. So there are a lot of satisfying results that stem from using the Bayesian method. Hey guys, and welcome back to this class, Bayesian Machine Learning in Python, Part 1. In this lecture, we are going to go back to our discussion on p-values and ask, is there a threshold we can come up with for Bayesian A/B testing? Even though Bayesian sampling is very efficient, it still uses up resources. You would presumably have to store your values of A and B in a database somewhere, and you'd have to generate random numbers for all your bandits and so on. So if you're certain one advertisement is better than another, why not just display that advertisement in a static way? In this lecture, we are going to discuss a specific probability measure, in particular, the probability that mu1 is greater than mu2. Remember that mu is the click-through rate. Also remember that mu1 and mu2 are both beta distributed. Before we calculate this probability, let's once again look at the definition of p-value. Recall how confusing it was, how much controversy there is concerning it, and how easy it is to phrase things the wrong way and make a statistician angry. Remember that you can't accept the null hypothesis. You can only not reject the null hypothesis. With definitions like that, it's easy to see why so many people love machine learning when statistics never got as much attention, even though they are both pretty much the same thing. Now, I said earlier that it's easy for non-technical people to misunderstand what p-values mean, and it's easy for things to get lost in translation. A common misconception is that, say you get a p-value of 1%, then that means the probability that mu1 is not equal to mu2 is 99%. Using the definition above, this is of course not the case. And yet people want a probability like this. It's simple and it's easier to interpret, and everyone can understand it. Luckily, because mu1 and mu2 have distributions, Bayesian methods allow us to calculate it. The question now is, how do we do that? Let's start with the basic premise. We want the probability that mu2 is greater than mu1, which is the same as the probability that mu2 minus mu1 is greater than 0. If we let x equal to mu2 minus mu1, then we have p of x greater than 0, which would be the area under the PDF of x from 0 to infinity. What we don't know is the distribution that x has. Instead of doing that, we'll take an alternative route. We'll look at the joint PDF of mu1 and mu2 and find the area under the curve where mu2 is greater than mu1. The joint PDF is just the multiplication of the two betas since they are independent. In fact, you can make a plot of the joint PDF as a heat map or image, so we just want the area of the upper triangle. Now the derivation is outside the scope of this course, but the end result is this closed form expression, which can easily be solved by a computer. However, note that the summation is O of A2, so it's not necessarily fast to calculate. Another option for getting a threshold is to define a loss function and then quit when the expected value of the loss falls below some threshold. Assuming that mu2 is greater than mu1, we can define the loss function to be the max of mu2 minus mu1 and 0. Next, we can calculate the expected value of the loss under the joint distribution, and then we stop when the expected value of this is less than some threshold. So we can calculate the expected value of the loss under the joint distribution using this integral. Now the integral looks complicated, but you can solve this by making use of the previous integral, which is much harder. So I would recommend giving this a try as an exercise. So it's possible to define thresholds for Bayesian A/B tests, although in the next lecture, we'll look at how using Bayesian A/B testing will let us converge to the maximum click-through rate automatically without actually stopping the test. Also, keep in mind that using the Bayesian method still does not bar you from using a traditional A/B test as well. The data is all there, so there's nothing stopping you from plugging it into a regular A/B test and getting the p-value and so on.